Welcome to the Explainer. Let's just jump right in, because today we are tackling a highly technical overview of speculative decoding. If you're managing large language models in production, you already know the harsh truth. Raw compute isn't your biggest enemy. It's memory bandwidth. As we scale these models to hundreds of billions of parameters, standard autoregressive pipelines are literally crippled by the time it takes to just move data around. So we're going to explore a game-changing architectural technique designed to completely break the serial generation barrier and solve your inference latency problems at scale. We're talking about massive throughput boosts here. For instance, imagine achieving a whopping 5.73x speedup on Google's TPU v5p architecture. Now, I know that sounds a bit like magic, but as we'll see, it's really just brilliant systems engineering. It's all about finally keeping your hardware's matrix multiplication units sweating and fully occupied instead of just sitting around waiting for data to load. We're going to dig into exactly how you can replicate these kinds of numbers in your own deployments. We've got a packed blueprint for this explainer. We'll start by diagnosing the sequential generation bottleneck, then break down the exact mechanics of speculative decoding. After that, we'll look at how this boosts heavy hitters like Qwen, DeepSeek, and GLM before diving into hard framework and hardware benchmarks. Finally, we'll wrap up with a practical runbook for production tips and tuning.
All right, let's get into it with part 1, the sequential generation bottleneck.
To understand the solution, we first have to diagnose why your incredibly expensive GPUs are basically taking a nap most of the time. Standard autoregressive generation is entirely starved by memory bandwidth. Because it spits out just a single new token per step, the accelerator has to launch expensive matrix multiply kernels to do a tiny fraction of actual arithmetic work. Worse, it has to read the full KV cache from memory every single time it generates a single word. It leaves your actual processing engines largely underutilized. Speculative decoding completely flips this dynamic. It turns sequential memory lookups into a compute-dense, highly parallel workload. So how does this actually work under the hood? Let's break down the mechanics. The crucial concept here is decoupling. We are decoupling token drafting from token verification. Instead of forcing a massive 70 billion parameter target model to painfully generate every single word sequentially, we bring in a much smaller, lightweight draft model, maybe just 1 or 2 billion parameters, to guess a sequence of future tokens. Because it's tiny, it drafts incredibly fast. Then, the large target model takes all those guesses and verifies them all at once in a single, highly efficient parallel pass. There is a perfect analogy from the source material for this. Think of it like a meticulous chief scientist in a lab, relying on a less experienced but super fast assistant to handle the routine experiments. The assistant furiously drafts out the work, and the scientist just quickly checks it. And the true beauty of this system, we preserve exact output quality. This is a mathematically lossless acceleration method. If the assistant messes up, the scientist steps in, corrects it based on the exact same probability distributions, discards the bad work, and moves on. You get absolutely identical outputs, just way faster. Let's break that speculative loop down step by step. First, the draft model proposes K candidate tokens. Second, the target model steps up and verifies all K tokens in one single parallel forward pass. Finally, we do rejection sampling. We mathematically compare the distributions and accept the longest string of tokens that match the target model's probabilities. At the very first mismatch, boom, we immediately reject the rest, generate the correct token, and start the whole loop over again. Now, let's see how this actually boosts today's state-of-the-art open-weight models. The implementation landscape is evolving incredibly fast right now. Take DeepSeek-R1. It uses native multi-token prediction directly integrated into its architecture. It predicts multiple future tokens naturally per step. No separate draft model required. Then you have GLM and Llama leveraging Eagle 3's lightweight auxiliary prediction heads to bypass standard drafting constraints completely. Meanwhile, Qwen3 uses fuse speculation, compiling a highly aligned 1.7 billion parameter draft model right alongside the target model in memory. Basically, whatever stack you are running, there's a specialized approach ready to go. Check out this 2.26x speedup on DeepSeek using UAG-TLI for probabilistic decoding. This is fascinating because traditionally, speculative decoding requires the draft and target models to share the exact same vocabulary, which is a massive architectural headache. But Universal Assisted Generation, or UAG, breaks that constraint entirely. You can use any off-the-shelf model as an assistant, regardless of tokenization differences. And with the TLI extension, it now supports probabilistic sampling, not just
heterogeneous greedy decoding, driving these crazy speedups even on complex, non-deterministic tasks.
Let's anchor all this theory with some hard framework and hardware benchmarks straight from the speed bench evaluations.
These metrics absolutely prove the efficacy of speculative decoding across top-tier hardware configurations. We're looking at the massive Llama 3.1 405B model hitting a 3.61x speedup on a cluster of 4 NVIDIA H200s, or Qwen3-4B achieving that massive 5.73x boost on Google TPUs for intensive math reasoning. The data proves a fundamental architectural law here. The wider the gap between your memory bandwidth and your raw compute, the more speculative decoding can step in to reclaim that idle processing capacity. But remember, your hardware is only as good as your software. Choosing your serving framework matters immensely. VLLM is still the gold standard for multi-user APIs with continuous batching using paged attention to manage KV cache memory without fragmentation. SGLang, on the other hand, absolutely dominates if your workload relies heavily on prefix reuse, like RAG systems or multi-turn chat, because its radix attention treats the KV cache like a highly optimized prefix tree. And if you want absolute peak raw throughput on NVIDIA hardware, TensorRT LLM is your go-to, assuming you can absorb the upfront engine compilation time. All right, let's shift gears to our definitive runbook for production tips, tuning, and keeping things stable. To protect your throughput, you actually need to know when not to use speculative decoding. If you are compute-bound, which generally happens at concurrent batch sizes greater than 32, shut it off. At that point, your GPUs are fully saturated, and adding a draft model literally just steals precious compute cycles from your primary task. You also want to avoid it for very short sequences under 50 tokens or highly randomized high-entropy outputs, where your acceptance rates will naturally tank below 50% and create too much overhead. Now, what if your workload is highly variable? Say you're sometimes generating highly predictable code and other times creative text. Your acceptance lengths will constantly fluctuate. In this case, use SGLang's adaptive decoding. It automatically tracks your runtime token acceptance rates with an exponential moving average and dynamically switches between speculative step tiers like 1, 3, or 7. It continually optimizes your draft tree depth on the fly, all without needing to restart your server or touch your configs. If you are deploying with VLLM, you absolutely must configure this production auto fallback setting, -- speculative disable by batch size 32. This simple flag ensures that when massive concurrent traffic spikes hit your system, VLLM gracefully falls back to standard auto-regressive decoding. It handles the load spike totally transparently, preserving your latency targets under pressure with zero code changes needed on the client side. It is a lifesaver for stable deployments. One final pitfall, out-of-memory errors. Because speculative decoding requires loading 2 models simultaneously, OOMs are a common headache. If you hit one, follow the strict 4-step recovery recipe from the SGLang docs. Start by lowering your static memory fraction to manually reserve more VRAM for the KB cache. If it still crashes, reduce your coup de graph batch size. Still failing? Reduce your draft tree size. And if all else fails, limit your concurrent requests. I want to leave you with this final thought as you reevaluate your infrastructure. Take a really close look at your utilization metrics right now. If your high-end GPUs are sitting idle just waiting for memory transfers, you aren't just leaving performance on the table, you are quite literally burning money. So isn't it time your architecture started speculating?